Welcome back to the Deep Dive. Today, we are wrestling with, well, the hardest, fastest, and maybe the most foundational layer of this whole AI revolution,
Mm.
the infrastructure itself.
hmm
Look, if you're an infrastructure manager or, a technical decision maker right now, you're facing what these documents we looked at call a double challenge.
Yeah, it's a tough spot.
On one side, you've got this exponential potential of AI, all the amazing things it can do.
Transformative stuff.
But then on the other side, just exponential complexity and how you actually run it, scale it, keep it secure. It's a lot.
It really is. And that's our mission today, right? To take this, frankly, dense stack of technical documents, AI accelerators, special silicon system architectures, and sort of break it down.
Make it actionable.
Exactly. Actionable knowledge. We're focusing on that strategic shift, moving away from the old general purpose hardware towards these specialized solutions.
Because you have to.
You have to. The goal is making sure your AI systems are efficient, effective, secure, and that really starts with understanding this hardware specialization piece.
Okay, so where do we start? We almost need an analogy here because the old one-size-fits-all hardware idea for AI, it's basically obsolete now.
Completely. Yeah, the analogy that popped out from the sources is thinking about the early days of the automobile.
Okay.
Think way back, start of the 20th century. When cars first appeared, every single one was basically a mechanized carriage.
Right. Same basic parts, same design.
Exactly. Standardized parts, standard architectures. But that standardization, it broke down really fast as demand grew, and more importantly, as uses diversified.
Yeah, you wouldn't use the same carriage for a race as you would for hauling freight.
Precisely. You don't use that standard carriage to race or to deliver heavy stuff or for an emergency rescue. Modern AI, it's exactly the same situation.
So it needs different tools for different jobs.
It requires differentiated solutions. You need the specialized ambulance, the race car, the truck of computing power, the silicon, the hardware itself. It must be optimized to match the specific workload, the specific job requirement.
And if you don't match the hardware to the job, that's where the problems start. You run right into this central strategic challenge, right sizing. It sounds simple, right sizing, but the risks, if you get it wrong, they're huge. It hits performance, it hits the bottom line.
Oh, absolutely. The risks are kind of a binary choice, really, and both ways are costly failures. If you underdimension your system,
Meaning too small, too slow.
yeah, you pick hardware that's too small, maybe it doesn't have the memory bandwidth you need, or it's just too slow for the latency required. You might get a fast answer back, but that answer, it could be false.
Ooh.
Or incomplete, or just plain risky. Imagine like an automated trading system making a huge decision based on analysis that, whoops, skipped some data points because the compute was overloaded.
The cost of that failure is
Yeah,
astronomical.
say.
So that's underdimensioning. What about the other way? Overdimensioning. This feels like maybe the more common reaction, right? Just panic and throw money at it.
It often is. That panic reaction, okay, I'll just get the biggest, most expensive hardware I can find, throw it at the problem, make sure I have enough headroom.
Cover all bases.
Right. But the documents we reviewed, they're really clear on this. This constant, unnecessary reliance on these massive, huge models running on oversized general-purpose GPUs, it's just not cost-effective.
And not sustainable.
Not sustainable in a real production environment.
Yeah.
And it gets worse.
How so?
Because this over-dimensioning, it risks what the documents call kneecapping other critical systems.
Kneecapping, that sounds dramatic.
It is, but it's not just a metaphor for spending too much money. It's a technical failure.
Okay.
By tying up massive resources, compute, memory, interconnect, bandwidth on tasks that could have been handled by a smaller, more specialized unit, you literally starve other essential systems, systems that aren't even AI.
So you're slowing down the rest of the business.
You're saturating those high-speed interconnects. Think NVLink or specialized fabrics, which impacts memory sharing for everyone, increases latency jitter for like essential admin and management processes. That collateral damage, that's the technical definition of kneecapping.
Okay, so the big takeaway right up front is these AI hardware accelerators, they aren't just nice-to-haves. They're the strategic tool you need to implement this right-sizing properly.
Precisely, to get the efficiency without causing this kind of systemic failure.
All right, so let's dive in. We need to unpack how they actually do this, where they physically live in your server rack, and, interestingly, how this even connects to things like data privacy on your own personal systems. Okay, let's get architectural for a minute. Before we dive into the nitty-gritty of silicon differences, we need a common picture, right? A framework.
Yeah, a simplified view helps. We can think of any running AI system as having basically three conceptual layers. A stack.
Layer 1 at the top.
That's the software. This is your application management layer. It handles governance, things like bias detection, ethics policies, and security, which is really about data protection, access control, that kind of thing.
Got it. Software on top. Middle layer.
That's the models, the actual AI logic, the learned intelligence, the algorithms. You could say it's the brain of the operation.
And holding it all up, the foundation.
That's the infrastructure or hardware. Everything from data input to the final output relies on this layer. And this is where those specialized AI accelerators live. They're the engine room.
Providing the raw compute power.
The brute force compute, exactly. So an AI accelerator, fundamentally, is purpose-built hardware. It's specialized silicon.
Designed for one thing.
Optimized specifically for the complex math that AI workloads depend on. We're basically talking about doing matrix math, linear algebra, tensor calculations really, really efficiently and in parallel.
And that's where the advantage comes in, compared to just using a standard CPU, right? General purpose hardware.
Huge advantage. Because these accelerators are designed only for this kind of intense, repetitive math, they just blow general purpose CPUs away. Orders of magnitude faster.
Faster and...
Significantly lower power consumption, and a smaller physical footprint. It's a trifecta.
How do they do that? What's the magic inside?
It's down to the microarchitecture. They optimize mainly two things: parallelism and memory bandwidth.
Okay, parallelism first.
Neural networks need vast numbers of calculations to happen all at once, simultaneously. These chips are designed literally to handle streams of computations in parallel. It gets rid of the sequential bottlenecks you find in traditional CPUs.
And memory bandwidth, getting the data in and out fast enough.
Crucial. They have optimized very wide memory interfaces to feed those parallel processing units constantly. High bandwidth memory, or HBM, is often part of the package for the bigger accelerator. Keeps the engines fed.
Now, you mentioned nomenclature earlier.
Yeah.
For the technical folks listening, we need to be clear on the terms. AI card versus AI accelerator card. They sound similar.
They do, and they're often used interchangeably, which can be confusing. An AI card is sort of the general term, often vendor-specific. It's basically any piece of hardware you plug in to speed up AI tasks, usually a physical PCIe card.
Okay, the generic term.
Right. But an AI accelerator card, that's the specific subset we're really focusing on here, the one the source material emphasizes. Its architecture, the silicon itself, was designed and made from the ground up for specific KI or AI tasks.
And there's a key distinction within that.
A really crucial one for planning. Is it designed primarily for training or for inferencing?
Why is that distinction so vital?
Because training and inferencing have fundamentally different demands on the hardware.
Okay, break that down. Training.
Training a big model, like a foundational LLM, that needs massive data sets. It requires extremely high floating point precision, often 32-bit, sometimes even higher, because you're doing trillions of calculations and tiny errors can accumulate.
Right, accuracy is paramount during training.
Absolutely. And you need enormous memory bandwidth to constantly feed the model new data batches. Shovel data in fast, keep the math precise. That's training.
And inferencing. That's running the already trained model, right?
Exactly. Inferencing is using the model to make predictions or generate outputs. Here, the priority shifts. It's all about speed and low latency. Get the answer back quickly.
So precision maybe isn't as critical?
Often not. Inferencing can frequently use lower precision math, like 8-bit integers, INT8. It's much faster, uses way less power, and often the tiny hit in absolute numerical accuracy is perfectly acceptable for the final result.
Different needs, different optimal hardware. Makes sense.
Totally different designs are optimal.
Okay, so let's walk through the hardware spectrum then. From the more general stuff that got repurposed to the really specialized silicon, keeping training versus inferencing in mind.
Sounds good. Starting on the, let's say, repurposed or more general side, the obvious one is GPUs, graphics processing units.
Which weren't originally for AI at all.
Not at all. They were for making video games look good. But graphics rendering also relies heavily on linear algebra and parallel processing. So they got leveraged for AI because they were available and offered that high parallelism.
Good for general training, maybe?
Yeah, they became the workhorse for a lot of training, but they can be overkill, inefficient, or just too power-hungry for many simpler inference tasks.
Okay, what else is in that sort of flexible category?
FPGAs. Field Programmable Gate Arrays.
Programmable after they're made.
That's the key. You can reconfigure their internal logic. This makes them super flexible, great for tasks where the algorithm might change or if you need some kind of custom non-standard numerical precision. They offer a middle ground, more efficient than a CPU for certain tasks, but more flexible than a dedicated chip.
Sort of a hardware Swiss Army knife.
Kind of, yeah. Good for offloading specific functions from the main CPU too.
Okay, now let's shift to the truly purpose-built category, the specialized accelerators. This is where we see those big architectural changes for maximum effectiveness.
Exactly. This is where the design is laser-focused on AI math. The flagship example here is probably the TPU, the Tensor Processing Unit, which Google really pioneered.
Optimized for tensor operations, as the name suggests.
Right. And to get that efficiency, especially for inference, it uses a clever design called a systolic array.
Systolic array, how does that work?
Okay, think of it like this. Instead of a standard architecture where data moves back and forth to a central processing unit, a systolic array passes data through a grid, like a network, of simple, tightly coupled arithmetic units. Each unit does a small calculation and passes the result to its neighbor.
So the data flows through the processors.
Precisely. It dramatically cuts down on data movement, which is a huge bottleneck for latency and power consumption, especially for those really repetitive matrix multiplications that are core to deep learning inference.
So the architecture itself is fundamentally different, built for AI math, unlike just repurposing a graphics card.
That's the key difference. It's designed for the data flow of AI algorithms.
Okay, TPU. What else is purpose-built?
You have NPUs, neural processing units. You often find these integrated into smaller devices at the edge. They're designed specifically to mimic neural network functions, with a real emphasis on low-power, high-speed inference. Think mobile phones, cameras.
Got it. And the most extreme end of specialization?
That would be ASICs. Application-specific integrated circuits.
Application-specific, meaning built for one job only.
Exactly. These are the absolute kings of single-task efficiency. You literally design the specific computation pipeline you need and etch it directly onto the silicon. You throw away general-purpose instructions entirely for maximum speed and minimum power on one specific task.
Wow. Sounds expensive to design.
Very expensive to design and fabricate, and they have zero flexibility. If the task changes, the chip is useless. But if you have a massive scale, completely fixed workload, like, say, hyperscale inference for one specific family of models, nothing beats their efficiency per watt or per dollar over the long run.
Okay, so we have this whole spectrum. Flexible FPGAs, powerful but general GPUs, specialized TPUs and NPUs, and ultra-specialized ASICs. For the system architect looking at all this, what's the ultimate metric? It can't just be raw speed or lowest cost, right?
No, the key enterprise metric, the strategic one, is effectiveness.
Effectiveness, define that.
It's really a combination metric. It blends accuracy is the answer the AI gives correct, reliable, trustworthy. With performance, did we get that answer fast enough to actually be useful in the context of the business process?
So getting a super fast wrong answer isn't effective. Getting a perfectly accurate answer too late isn't effective either.
Precisely. Specialized hardware lets you tune that balance. It allows you to maximize effectiveness exactly where your specific use case demands it, instead of just settling for a general-purpose compromise that might be okay at everything but great at nothing.
Okay, so we've established we have this diverse toolkit, right?
Yeah.
Specialized engines for different jobs, flexible FPGAs, hardcore ASICs, everything in between. The goal then, architecturally, isn't to make everything uniform. It's the opposite.
Exactly. The goal is to build a heterogeneous system, a deliberate mix of these specialized engines, each optimized differently.
Why heterogeneous? What does that buy you?
It buys you flexibility and the ability to scale efficiently. Real-world AI systems don't just run one model doing one thing. They run maybe hundreds of different tasks, different models, all at the same time with different needs. A heterogeneous system lets you match the right engine to the right task.
And it helps with that right sizing and TCO, total cost of ownership, we talked about?
Absolutely. You use the efficient low-power chip for the simple tasks and the big, powerful chip only when you absolutely need it. That minimizes your overall operational cost.
Okay, so we're building this mix of accelerators. Where do they physically go in the system? Does it matter where they sit in the server or the mainframe?
Oh, it matters hugely. Where that accelerator physically lives is not just incidental packaging. It directly dictates critical factors like latency, power draw, and crucially, its access speed to memory, especially the CPU's cache.
So location, location, location.
Pretty much. The deployment documents we looked at detail 3 main integration options based on physical location.
Let's start with the closest, the fastest one. The one for absolute lowest latency, like for real-time decisions.
That's the on-die accelerator, sometimes called on-chip. These are literally integrated directly onto the main processor chip itself, right alongside the standard CPU cores.
Sharing the same piece of silicon.
Exactly. And the benefit is massive for latency. They are physically closest to the CPU cores, and critically, they often have direct, high-speed access to the CPU's level 1 and level 2 cache memory.
Which means less data travel time.
Way less. It minimizes data having to go off chip over a slower bus. This drastically reduces the communication pathway, cuts down on bus contention. It gives you the absolute best performance for extremely time-sensitive tasks, especially those using smaller models that fit within that cache proximity.
Okay, on-die for ultra-low latency. What's the next step out? Still inside the box, but maybe not right on the CPU chip.
That would be the in-system accelerator. This is located somewhere else on the main system board, maybe on a separate chip or a small module, but it's not resident on the main CPU die itself.
Still pretty close, though.
Still close. They're often connected using advanced chip-to-chip interfaces. Think specialized fabrics or high-speed links like CXL Compute Express Link.
CXL allows memory sharing, right?
Yeah, that's a key benefit of things like CXL. It allows for coherent memory sharing between the CPU and the accelerator, which is really powerful. These in-system accelerators need their own power budget, typically, but they offer a necessary separation for more substantial tasks, things that might otherwise bog down the main CPU if they were running on die.
Right, so you get some isolation. Okay, on-die, in-system. What's the third option
Yeah.
for the really big stuff?
That's the external accelerator. This is what most people probably picture when they think of an AI card. These are typically those large PCI cards you slot into a server.
Or even bigger systems.
Or increasingly, yes, dedicated external boxes or systems connected via ultrafast I/O. Think specialized fabrics again, or high-speed Ethernet like Rho-C. The key thing about external accelerators is that they often possess massive amounts of their own dedicated memory, especially that high bandwidth memory, HBM we mentioned.
They have their own private memory pool.
Exactly, and their own significant compute capacity. This completely decouples the workload from the host CPU's constraints, like its thermal limits or power budget. If you're doing something huge, like training a foundational model from scratch, you absolutely need external accelerators, probably lots of them networked together.
Okay, so on-die, in-system, external. 3 locations, trading off latency, power, cost, and capacity. Now, how do we connect this choice of physical location back to the type of AI model we're running? You mentioned earlier there are sort of 2 big families of models with very different resource needs.
Right. Broadly speaking, we can categorize them into traditional KI, which covers classic machine learning, ML, and deep learning, DL, and generative KI, or Gen AI.
Okay, traditional KI first. What are its characteristics?
Traditional KI models are typically characterized by being relatively fast to run, often smaller in size, and generally quite stable once trained. They're used for specific predictive analysis tasks, things like classification. Is this email spam? Regression? What will sales be next quarter? Clustering.
The workhorses.
Exactly. They're the cost-effective workhorses for many, many enterprise tasks. And because they are often fast and small, they are perfect candidates for running efficiently on those lower power, lower latency options.
Ideal for on-die or in-system accelerators.
Often, yes. Especially for inference where speed is key, you can deploy them very cost-effectively.
Okay, then we have the new kid on the block, the one getting all the headlines, generative KI, Gen AI.
Right. And Gen AI models are almost the opposite in terms of resource demands. They're defined by massive complexity, huge size, often billions, even trillions of parameters. They require vast amounts of memory, especially HBM, to hold those parameters.
And lots of compute power.
Sustained, high-precision compute, especially for training, but even inference can be demanding. Their purpose is different to sophisticated generation, text, images, code, complex reasoning, acting almost like consultants.
But the drawback is?
The drawback is they carry a significantly higher energy requirement and a much higher operational cost premium. Running a big Gen AI model 24/7 is expensive.
So for these monsters, you pretty much need the big guns.
For Gen AI, especially large ones, you almost always need the high capacity, the dedicated memory, and the raw compute power of an external accelerator. Trying to run a massive LLM on a small on-die accelerator just isn't feasible.
This is really important then. Because if traditional KI, the smaller, cheaper stuff, is still highly effective for a lot of common business tasks, like classification, we shouldn't just jump to using expensive Gen AI for everything just because it's new and exciting.
Absolutely not. That's a crucial strategic mistake. The whole point of building this heterogeneous architecture is precisely to avoid that costly trap. You don't want to run a simple spam filter task on a multi-billion parameter Gen AI chip that costs a fortune to operate.
It comes back to that instructional chain you mentioned.
It's fundamental for any technical architect or manager making these decisions. Amendungsfall, the use case. What problem are you actually trying to solve? That dictates the model size and type needed. And that choice then dictates the optimal hardware accelerator and its location.
Use case beyond model hardware.
Always in that order. Don't start with the hardware and try to fit the problem to it.
And this isn't just about getting the best performance. It's about the money, the total cost of ownership.
Exactly. You're constantly trading off the initial purchase cost, the capital expenditure, CapEx, against the long-term running costs, the operational costs, OpEx. And OpEx for AI hardware is dominated by two things: power consumption and the cooling needed to handle that power.
Which can be huge for big accelerators.
Massive. So running a simple inference task on a tiny optimized NPU that sips power, instead of letting it run by default on a massive external GPU that guzzles electricity. That difference can literally save you thousands, maybe tens of thousands of dollars in operating costs per year, especially when you deploy at scale.
So 2 more key metrics for the hardware manager to track: TCO and power density. How much power are you packing into each rack unit?
You got it. You have to select hardware that fits not just the performance profile for the use case, but also the entire cost structure and the physical constraints of your data center: power availability, cooling capacity, rack space. Optimized, specialized silicon isn't just technically elegant, it becomes a long-term financial imperative.
Okay, let's make this really concrete. We're moving from the theory of heterogeneous systems to how you actually implement it strategically. Before you even pick a piece of hardware, the architect needs to answer some fundamental questions about the job itself, right?
Absolutely. You have to quantify the strategic requirements first. Key questions are: how much risk is tolerable in the outcome? What specific inputs are available to the AI? And critically, what latency, what speed is actually required?
That latency question seems key for deciding where the accelerator goes.
It's often the deciding factor. Do you need a sub-millisecond response, like for high-frequency trading or maybe real-time industrial control? Or can you tolerate a few seconds, maybe even minutes, like for summarizing a long document overnight?
Big difference.
Huge difference. And this requirement is what often drives the need for these sophisticated multi-model or ensemble KI systems, systems that use several different models working together.
And these ensemble systems only really work efficiently in that heterogeneous hardware environment we've been talking about.
Exactly, because different parts of the ensemble have different needs.
Okay, let's walk through the case study from the documents. Credit card fraud detection. This seems like a perfect example because it needs to be fast, it needs to be accurate, it needs to be always on, but it also has to be cost-effective at massive scale.
It really ties it all together. This system, as described, is deployed using a strategic two-stage process. It's deliberately designed to optimize for both latency and risk tolerance, using different models on different hardware.
Okay, stage 1. This handles the bulk of the work, right? The millions of transactions happening constantly. What's the focus here?
Stage 1 focuses on speed and acceptable risk. The core task is simple. Based on immediate data, does this transaction look statistically like high-risk fraud? Yes or no?
And it has to be incredibly fast.
Extremely low latency is non-negotiable. The customer is literally standing there waiting at the point of sale. You can't have seconds of delay.
So what kind of model and hardware for stage 1?
For this, the system uses a fast, small, probably traditional KI model, maybe a lightweight decision tree, or a simple neural network trained for rapid binary classification. It might achieve, say, an 80% success rate in catching obvious fraud or confirming legitimacy.
So it accepts that 20% will be uncertain.
Exactly. The risk is managed by knowing that 20% of cases will need a closer look and get escalated to stage 2. Now, the critical hardware choice for stage 1, this task is assigned to an on-chip accelerator.
Back to lowest latency option. Why is that so crucial here?
It's pure physics and data locality. The transaction data amount, location, merchant ID, it's probably already sitting right there in the main processor's L1 or L2 cache because the transaction just came in.
So the data is already close.
Right. By pulling that small, fast classification model and the necessary logic immediately onto the on-die accelerator, you avoid any latency penalty from going off-chip, across a bus, or, God forbid, over a network connection.
Milliseconds matter here.
Microseconds matter. You get immediate validation. This maximizes throughput for the millions of simple transactions and, importantly, minimizes latency jitter.
Jitter being the variation in response time.
Exactly. You need predictable, consistently low latency for this kind of high-volume processing. So stage 1 uses the absolute minimum resource the on-die accelerator needed to make that quick, 80% accurate decision instantly.
Okay, stage 1 handles 80% of transactions on the fast, cheap on-die accelerator. What happens to the other 20%? The ones that fall into that, maybe suspicious, maybe okay bucket?
Right. They're too complex or ambiguous for the simple stage 1 model to call confidently. But you can't just reject them all. That would be terrible customer service. You also can't just approve them blindly.
So they need a deeper look.
They trigger stage 2,
Yeah.
deeper analysis. This stage prioritizes high complexity and high accuracy. The goal here is to drastically reduce false positives, blocking legitimate transactions, and catch sophisticated fraud missed by stage 1.
So a different kind of model is needed.
Definitely. Here, the system invests the resources in a larger, much more computationally intensive Gen AI model.
Why Gen AI here?
Because it can perform deeper analysis, it might pull in and reason over external behavioral data, the customer's past purchase history, geographical patterns, device information, maybe even unstructured text data associated with the account. It's looking for subtle anomalies a simple model couldn't see.
Okay, a powerful model.
Yeah.
Where does it run? Not on die, presumably.
No, that would defeat the purpose. This complex, slower Gen AI model requires more memory, more compute cycles, so it gets assigned to either an in-system accelerator, if moderately complex, or, more likely for a really deep analysis, an external accelerator, a dedicated high-power card, probably with its own HBM memory pool.
And the genius of this architecture is the separation.
Right, that's the key strategic insight. By directing this uncertain, complex 20% of cases to the separate, more powerful hardware, the system achieves two critical things. First, it gets the high accuracy needed for these tricky cases. Second, it prevents that massive Gen AI model from causing the kneecapping we talked about.
It doesn't block the main highway.
Exactly. It doesn't block the performance-critical on-die engine that's busy handling the continuous stream of millions of simple stage 1 transactions every second. The architecture acts like an intelligent traffic cop.
Directing requests based on need.
It directs the request to the most suitable available resource. The bigger Gen AI model is allowed to take a bit longer, maybe 500 milliseconds instead of 50 microseconds, to achieve that near-perfect accuracy on the difficult 20%. But it does so without degrading the performance or responsiveness of the overall system for the other 80%.
So the conclusion here is that this kind of sophisticated multi-model ensemble approach it's really only efficient if you have that underlying heterogeneous system of accelerators.
It's the only way to make it work efficiently at scale. Each accelerator is tailored to its specific operational task within the larger workflow, some for speed, some for accuracy, some for massive capacity. It's strategic planning made real in silicon and system design.
Okay, we spent a lot of time on the compute side, making the calculations faster with specialized hardware. But AI inference, especially with these big models, quickly runs into another major bottleneck, the data itself, what the sources call the data gap.
Yeah, this is huge. AI models, particularly the big Gen AI ones, they're trained on massive data sets, but that data is frozen at a point in time. To give truly precise, relevant, and trustworthy answers now, they need access to timely external information that wasn't part of their original training.
Like current company data or recent news.
Exactly. Think about asking an AI assistant about company policy. If it was only trained on data from 2 years ago, its answer might be dangerously out of date. It needs access to the current policy document.
It knows general stuff but lacks specific up-to-the-minute context.
Precisely. It knows general facts about the world, but it lacks the contextual relevance that's unique to your organization or your specific question right now, or the data that changed 5 minutes ago.
So the mechanism developed to bridge this gap, to feed the model current context, is RAG, Retrieval-Augmented Generation.
That's the one. Array is essentially a clever process that allows the AI model, before it generates its final answer, to first retrieve relevant snippets of information from external, up-to-date data sources.
And it stuffs that retrieved info into the prompt?
Basically, yes. It augments the original prompt with this fresh, relevant context. This helps guarantee the model's final output is current, accurate, and grounded in specific facts, not just its generalized training knowledge. Makes the answers much more trustworthy.
Okay, RAG sounds great. Problem solved.
Well, Array immediately slams into a massive practical obstacle: the format of most useful data.
Ah, Not nicely structured database tables.
Unfortunately, no. Most of the really valuable corporate and proprietary data the stuff already needs to access is completely unstructured. We're talking about mountains of PDFs, Word documents, PowerPoint presentations, emails, audio call transcripts, video meeting summaries, maybe proprietary research papers, all locked away behind the corporate firewall.
A mess of different formats.
A huge, messy pile. And standard databases, standard search indexes, they just can't effectively find or extract the specific context needed from within that unstructured mess. They might find keywords, but not meaning.
So the solution isn't just another compute accelerator. We need something for the data side. We need specialized storage.
You'll need specialized storage architecture, yes. The strategic solution emerging here is content-aware storage, or CAS.
Content-aware storage, what does that mean?
CAS is designed to be an integral part of that RAG pipeline. It's not just about storing files, it's a system that actively uses techniques like natural language processing, NLP, to understand and extract higher value, deeper meaning from those existing, messy, unstructured data stores.
Making the data understandable to the AI.
Essentially, yes, making the data semantically meaningful, not just physically accessible bytes on a disk.
And the absolute crucial function here, the thing that makes CAS different from just, say, a really good enterprise search engine, is what the documents call the semantic key.
Yes, the semantic key concept is vital. A traditional keyword search just finds exact word matches. Driving finds driving.
But it doesn't know what kind of driving.
Exactly. CAS has to understand semantic meaning. It needs to grasp the contextual difference between driving a car, which is about transport, and driving a hard bargain, which is about negotiation. Same word, totally different meaning.
How does it do that? How does it capture meaning?
It achieves this primarily by transforming human language words, sentences, paragraphs, even whole documents into mathematical representations called vector embeddings.
The vectors, like in math class.
Sort of, yeah. These are high-dimensional vectors, points in a complex mathematical space. The key idea is that pieces of text with similar meanings get mapped to points that are close together in this vector space.
So meaning becomes proximity.
Exactly. The distance between vectors represents semantic similarity. If the AI can't accurately retrieve the contextually relevant information based on meaning, not just keywords, then the RAG process fails, and the final output will be inaccurate or nonsensical. Garbage in, garbage out, amplified by AI.
Okay, so to actually build this content-aware storage system and make RAG work effectively at scale, you need more than just clever software. The documents outlined 4 core interdependent components that have to work together.
That's right. It's an orchestrated system. First, at the foundation, you absolutely require AI-optimized storage.
What makes storage AI optimized?
It needs to be resilient and scalable, obviously. But critically, it must be designed for massive data throughput, especially for the kind of non-sequential parallel access patterns common in AI data processing and vectorization. Traditional storage systems designed for sequential reads and writes will just choke and become a huge bottleneck.
Okay, fast parallel storage foundation. Component 2.
You need well-defined AI data pipelines. These aren't just pipes. They are managed structures that handle the secure, efficient flow of data, ingesting new documents, cleaning them, vectorizing them, feeding the vector database. They need to minimize those traffic jams we talked about, ensuring smooth, low-latency data movement.
Got it. Storage, pipelines. Component 3 must be the vectors themselves.
The heart of the semantic key, vector databases. These are absolutely essential for efficient RAG. They don't index text strings like a normal database. They index and organize those high-dimensional vector embeddings we just discussed.
How do they search based on meaning then?
Their core mechanism is calculating the mathematical distance or similarity between vectors, usually using something like cosine similarity. When you search, you provide a query vector representing your question's meaning, and the database instantly finds the stored vectors that are closest to it in that multidimensional meaning space. Those closest vectors correspond to the most semantically relevant documents or passages.
Super fast meaning-based retrieval. Okay, that's 3. Storage, pipelines, vector databases. What's the 4th component? We seem to be back at hardware.
We are, because even with clever databases, doing that similarity search, calculating cosine similarity across potentially billions of very high-dimensional vectors for every single user query is an incredibly compute-intensive mathematical operation.
So you need acceleration for the search itself.
Exactly, and also for the initial process of turning the documents into vectors in the first place, embedding generation. So component 4 is hardware acceleration. You need specialized chips, often GPUs, but potentially other accelerators too dedicated to rapidly accelerating these intensive vector math operations.
Without the hardware acceleration, RA would be too slow.
Way too slow to be practical for real-time Q&A or assistant-type applications. The user would be waiting forever for the system to find the relevant context.
Okay, so when you put all four together, the optimized storage, the efficient pipelines, the smart vector databases, and the dedicated hardware acceleration, then you get a system that can actually deliver on the promise of R.
That's the integrated picture, and that enables those practical CAS use cases we need, getting faster, much more precise, contextually grounded responses from AI assistants, ensuring trustworthiness because the models are using the latest proprietary data, and powering search results that genuinely understand user intent, not just keywords. It makes the AI much, much smarter in practice.
Right, let's pull back to the big picture for the infrastructure manager again. The complexity is just mind-boggling. We talked about heterogeneous hardware, different models, array, different locations. They're facing what the docs called a many-to-many challenge, aren't they?
That's a great way to put it. It's not a simple one-to-one mapping. A single strategic business use case, let's say complex financial modeling, might end up needing, I don't know, 4 different AI models working together.
Like an ML model for prediction, maybe an NLP model for sentiment from news feeds, a big Gen AI for scenario generation, and AirAg to pull in current market data.
Exactly. And those 4 models, in turn, might need to run across a whole pool of maybe 5, 10, or even more different physical accelerator cards, some on-die, some in-system, some external GPUs, maybe even some FPGAs for specific pre-processing.
And which card runs which model depends on.
Depends on their real-time load, their current availability, the specific latency requirement of that particular step in the workflow. The whole logistical map is completely nonlinear, and it's changing constantly, minute by minute, as requests come in.
That sounds impossible for a human to manage optimally in real time.
It basically is. Trying to manually schedule workloads across that kind of complex, dynamic, heterogeneous environment is a recipe for inefficiency and bottlenecks. Which leads us to the next strategic layer, using AI to manage AI.
The orchestrator.
Exactly. The strategic deployment of agentic AI as the orchestrator, the traffic cop, the resource manager for the whole system.
Okay, agentic AI. What does that actually mean in this infrastructure context? How does it work?
Think of agentic AI not just as a simple automation script, but as a virtual system that has a degree of autonomy. It can perceive its environment, the state of the hardware, the incoming requests, make decisions, and take actions to achieve specific goals. Goals like maximizing throughput, minimizing latency for priority tasks, or reducing overall cost.
So it's like a virtual assistant manager for the hardware.
That's a good analogy. Maybe a very fast, very numerate assistant manager with continuous learning capabilities. Now, crucially, the agent itself doesn't usually run the heavy AI compute workload.
It delegates.
It delegates. It acts as the master scheduler. Its job is to decide in real time which physical KI card, which accelerator, and potentially which version of a model is best suited to handle a specific incoming task.
And bases that decision on.
On a whole set of factors. The task's requirements, latency, accuracy needed, the known capabilities of each hardware accelerator, the current load on each accelerator, power consumption constraints, cost policies, maybe even predicting future workloads. It's a complex optimization problem.
Okay, let's use another example. A really high-stakes, nuanced task like real-time regulatory compliance monitoring. This probably involves multiple models and different levels of urgency. How would an agent orchestrate this across the heterogeneous hardware zoo?
Okay, so a conference compliance request comes in maybe analyzing a new regulation against current business processes. The agent intercepts that request. First, it breaks it down and classifies the component tasks based on their urgency and complexity.
So step one might be just a basic check.
Right. The agent might decide that the standard check task, like does this transaction format meet the basic requirements of regulation XYZ, is a stable, fairly low urgency task. It checks its inventory and sees a general purpose GPU card on an in-system board has available cycles, so it sends the task there. Efficient use of a non-critical resource.
Okay, but what if the system detects something serious? An immediate, critical breach of compliance.
Okay, now urgency skyrockets. That becomes an acute reaction task. Something needs immediate analysis and potentially mitigation with absolute minimum latency. The agent recognizes this priority. It immediately routes that specific part of the request to the fastest resource available, the highly optimized, low latency on-die accelerator.
Using the race car only when needed.
Precisely. to guarantee that sub-millisecond response needed for critical alerting or intervention. Meanwhile, maybe there's another part of the original request, the report task, generating a comprehensive summary report of the whole compliance check.
Which isn't needed instantly.
Exactly, that's not time critical at all. The agent sees this, knows it can wait a bit, and decides to offload that task. Maybe it sends it to a pool of less utilized external accelerators, or even schedules it for batch processing on a remote server during off-peak hours to save cost.
This is genuinely intelligent resource management, isn't it? It's constantly juggling.
It is, because it's not just making one-off decisions, it's constantly monitoring the load across all resources. It ensures the high-value, low-latency accelerators aren't swamped with routine work. It intelligently reroutes tasks if one accelerator is busy or down. It might even use reinforcement learning techniques like Q-learning to learn over time the absolute most efficient pathways for different types of requests in this specific environment.
Balancing cost, speed, and utilization automatically.
Right. It ensures those expensive, specialized cards are only used when their unique capabilities are strictly necessary, maximizing the return on that hardware investment. It allows the whole complex system to scale and adapt much more fluidly and efficiently than human oversight alone could manage.
It turns the collection of parts into a truly cohesive, optimized system.
That's the goal.
Okay, that covers the massive enterprise scale, the data centers full of heterogeneous hardware managed by agents. But what's fascinating is that the same fundamental principles, understanding specialized hardware, needing orchestration, worrying about data flow, are now being applied by individuals, by technical users, for a very different, deeply personal goal: data sovereignty.
Yeah, this is the motivation behind the rise of the DIY private KI infrastructure, the home lab approach to AI.
Why are people doing this? What's the core goal?
It boils down to control, absolute control. People want to ensure their private documents, their sensitive prompts, their personal data never leave their local system. They want maximum security control, knowing their data isn't being scraped or used to train some external company's model.
And maybe just to understand the tech better.
That too, gaining that deep hands-on technical understanding of the entire AI stack from the hardware up to the model interaction. It's about empowerment through knowledge and control.
So the sources actually provided a pretty detailed breakdown of how you'd build such a DIY stack. It starts with fairly standard components, but uses them strategically, right?
Exactly. You typically start with a standard host environment, maybe Windows 11, maybe macOS, maybe Linux. But a common approach, especially on Windows, is running WSL2, the Windows subsystem for Linux.
Why WSL2 specifically?
Because WSL2 is critical for getting good performance. It provides a proper Linux kernel environment and, crucially, allows for native GPU pass-through.
Meaning the Linux environment can talk directly to your graphics card.
Yes. Your locally running AI models need that direct, low-latency access to the acceleration power of your gaming GPU or whatever card you have. Without GPU pass-through, running models locally would be painfully slow.
Okay, so WSL2 for the environment and GPU access.
Right.
What runs inside that?
You typically use Docker containers for virtualization. Docker is perfect for this. It lets you package up each service the environment needed to run the model, the user interface, into isolated containers.
Which gives you...
Isolation is key for security and manageability. It keeps dependencies separate, makes it easy to update components, and provides a crucial security layer between the services.
All right, so we have the container platform. Where do the actual AI models come from? We're not training foundation models at home.
No, definitely not. You're typically using smaller, often quantized versions of open source models like IBM's Granite or Meta's Llama 3, Mistral models. You source these pre-trained models from platforms like Llama or Hugging Face.
And Llama makes it easy to download and run them locally.
Yeah, Llama bundles the model and the execution environment needed to run it inference-wise within that Dockerized Linux environment using your local GPU.
So you can run the model locally. How do you interact with it? Just command line.
You could, but most people prefer a graphical interface. So a common pattern is to run a separate Docker container that provides a web-based graphical user interface. Something like OpenWebUI.
Okay, so OpenWebUI runs in one container, a Llama with the model runs in another.
Exactly. And OpenWebUI talks to the Llama container locally. This setup gives you a nice, familiar browser-based interface, similar to using ChatGPT online, but it's all running entirely on your own machine. You can select which local model you want to use, manage conversations, etc.
All private, all local.
All private. And this setup really shines when you bring in local RAG.
Ah, Retrieval-Augmented Generation on the home setup. How does that work securely?
It's surprisingly straightforward. The user typically keeps their private documents, financial records, personal notes, research papers, whatever, securely stored on a local NAS, a network-attached storage device.
Just a hard drive on their home network.
Basically, yeah. Cheap, resilient, local storage. Then using the Open Web UI interface, the user can point the system at specific documents or folders on their NAS.
And the system processes them locally.
Completely locally. The Open Web UI, working with the local Llama model and maybe a local vector store component, loads the content from the NAS, generates the vector embeddings locally, stores them locally, and performs the argue retrieval and inference using the local model and the local GPU.
So the sensitive documents never leave the private network.
Never. The context is retrieved from the NAS, fed to the model running on the local machine, and the answer is generated locally. The data is entirely sovereign. It never hits an external server, never goes to the cloud.
That sounds pretty secure. Is that the end of the story for the truly security conscious? Or is there one more layer of paranoia, let's say?
There's always one more layer for the truly paranoid. Even when you're using open source components, running everything locally, there's still a theoretical supply chain risk.
The risk being?
Risk of phoning home. The theoretical danger is that some component somewhere in that stack, maybe the model weights themselves, maybe the UI software, maybe some underlying library it depends on, might have hidden code that attempts to establish an external connection.
To send something out. Usage data. Snippets of prompts.
Potentially, yes. Metadata, telemetry, partial prompts. Even if it's not malicious, it might be undisclosed data collection that violates the user's goal of absolute sovereignty.
So, for the advanced user who wants to be absolutely certain nothing leaves, what's the countermeasure?
The ultimate step suggested is implementing a network tap or using dedicated packet-sniffing software to monitor all outgoing network traffic from that supposedly closed local AI system.
Watching the wire.
Literally watching the wire. Since the entire architecture is explicitly designed to be self-contained and operate offline, there should be zero legitimate reason for it to initiate external connections. If the network tap suddenly detects the system trying to make an unexpected DNS query or pinging an unknown IP address,
Alarm bells ring.
big alarm bells. The user is immediately alerted to the unauthorized connection attempt. It provides that final, ultimate layer of verification and control over data sovereignty.
Wow. It really demonstrates that whether you're managing a massive multi-million-dollar data center with agentic AI orchestrators or carefully building a private AI setup in your basement, the fundamental strategic principles are identical, aren't they?
They really are. It always comes back to understanding the hardware specialization, the need for orchestration, even if it's just you managing Docker containers,
Yeah.
and maintaining obsessive control over the data flow. Hack, outro.
So let's try and wrap this up. What does this all mean? If there's maybe one big strategic takeaway from this deep dive into specialized hardware, our age, agents, sovereignty, what is it?
I think the core takeaway is that the entire field, especially at the infrastructure level, is definitively shifting. We're moving away from just throwing generic brute force computing power at problems towards highly specialized, intelligently orchestrated systems. Efficiency, safety, managing TCO, getting the speed you need for modern AI. These things are no longer happy accidents or side effects.
They have to be designed in from the start.
They are the direct result of deliberate, strategic hardware planning. That right-sizing concept isn't just jargon, it's the fundamental requirement. You absolutely have to plan your infrastructure not based on just the general specs of the latest, greatest chip, but based on the specific, measurable requirements of the job you need done.
The latency needed, the accuracy required, the acceptable risk profile for that specific use case.
Exactly.
And it seems like that logic holds true regardless of scale. Whether you're that manager architecting a multi-billion-dollar fraud detection system for a global bank, or you're just tinkering in your home lab setting up a private AI assistant so your personal documents stay truly private. That instructional chain holds.
It's the absolute foundation. The use case, what are you trying to achieve? That must always define the model you choose. And the model's characteristic, its size, its needs, must then define the specialized, location-optimized hardware you deploy. Use case model, not hardware. Non-negotiable.
Okay, so that brings us to our final provocative thought for you, the listener, to mull over. We've established that agentic AI, these virtual managers, can successfully orchestrate all this complex, physical, heterogeneous hardware. They can decide where to send tasks, prevent bottlenecks, optimize latency, manage cost, all based on complex algorithms and learning.
Right, the agent as the scheduler, the resource allocator.
So here's the question. What if, in the not-too-distant future, The primary job of the senior IT decision maker, the infrastructure leader, isn't really about selecting which specific TPU or ASIC or GPU cluster to purchase.
What would it be instead?
What if their main strategic role becomes simply to hire, train, and then oversee the right agent, the right autonomous AI system to manage the entire complex, self-optimizing infrastructure automatically?
Shifting from managing hardware to managing the manager AI.
Exactly. What level of intelligence would that agent need? What kind of strategic insight? And maybe most importantly, what level of trust would that kind of autonomous system require from the human leaders ultimately responsible for it all?
That's a deep question about the future of IT management itself. Definitely something to think about.
Something to think about as this specialized silicon just keeps evolving at breakneck speed. Thank you for joining us for the deep dive.